Chapter 4 will be our next topic, which is probability. And we kind of take a break from what we've been doing in Chapter 3, discussing things like the mean and the standard deviation of a data set. So Chapter 4 is a bit different than the other chapters we do this semester. So we keep it pretty basic here with probability, just enough to sort of move us forward in our study of statistics. So let me just start with probability here in general. It's about assigning a number to the likelihood that an event will occur. And even in common day language, we're used to talking about probabilities and often in percent form when we're speaking. So if the chance of snow today in Long Beach is 0%, that means that is impossible. I'm pretty sure it's not going to snow in Long Beach, but it could, I guess, and that would mean the probability was slightly higher. And then, of course, at the other end, 100% chance, let's do an example. There's 100% chance that my dog will want to go for a walk today because I'm certain that he will. So probability in percent. And then just like proportions we started the semester with, probability as well can always be expressed as a percent, of course, but also in fraction or decimal form. And we tend to work in decimal form as we do math moving forward. So 0 for an impossible event and a probability of 1 for an event that's certain to happen. Okay, so what we'll do is consider 3 different approaches to probability, and each of them has its own place, which we'll talk about. But I just want to get something out of the way here on our graphing calculators when it comes to our calculator reporting a number that is a very small number, in our case, very small probability. So I just want to do this example. It says if 2,000 raffle tickets are sold and you purchase 1 ticket, what are your chances of winning the raffle? So even before I teach probability, this is sort of clear just because of the world we live in, that we would know that 1 ticket out of 2,000, I'm going to come to my calculator. So 1 ticket out of the 2,000 would be the winning ticket. This is an example of what we call classical probability or classical approach, which we'll talk more about. For now, though, my point is to see this entry appear on the calculator and knowing how to read that number. So what I'm going to do here in the notes is just rewrite that. So that E is actually a little bit smaller than the 5. You don't have to worry about writing it perfectly. But the idea here is this is our calculator's way of expressing a number in scientific notation. So you may remember when we multiply by a power of 10, it moves our decimal point to the left or to the right based on the exponent on that 10. So that E means that the exponent on the 10 is that value, which is -4. So when we have a multiplication by 10 to a power, that exponent tells you what you're going to do with the decimal point. I'm just going to draw a little red one there. So there's my decimal point now. That -4 means that you're going to move that decimal to the left 4 places. So that's what that means. So we move the decimal left because the number is negative. So left 4 places. And then the missing digits will be replaced with zeros. So I'll just draw some little swoopy lines here. So 1, 2, 3, 4, 4 places. And then those missing digits would be filled with 0. So 5e -4, which is 5 times 10 to the -4, would be equivalent to 0.0000 and then the 5. Okay, so we need to be on the lookout for values that have an E at the end. And remember that probability in decimal has to be a number from 0 to 1. So 5 can't be a probability anyway. So you would know to be looking for that E -4 or some E value at the end to determine how to move the decimal. All right, so this is going to come up in different spots during the semester. So I just wanted to do one more here. It says if the chance of rain today is 0.9999875, so getting very close to 1. So it's almost a guarantee that it's going to rain, not quite. So 1 is 100%, but pretty high. So if we take 1 and subtract that probability, we'll learn later there's a rule for that. The rule has a name. It's called the rule of complementary events. Not to worry about now, but just knowing that when we take 1 and subtract the probability of something happening, we end up with the probability that it doesn't happen. So I'm just typing that. And then again, you'll see your calculator switch to scientific notation. So when we see that 1.25 and then that e negative 5, so that's 1.25 times 10 to the negative 5, which means we're going to move that decimal point left 1, 2, 3, 4, 5 places. So when the exponent is negative on that 10, decimal goes to the left. So that's going to be 0.0000125. So that's an incredibly small probability. And all those zeros there are the reason that the calculator switches to scientific notation. So it's not having to use that line to put a whole bunch of zeros in front of it. So scientific notation is just shorthand so that we can save ourselves writing a bunch of zeros. All right, so that may not come up for a bit, but it's just good to get that out of the way, and then we'll go on to probability here. So I'm going to start with this approach called personal opinion approach or subjective probability. And this approach is really the simplest in practice because it really is just based on your personal opinion. I'm going to do myself as an example. So if I had to estimate the chances that I will adopt a puppy in the next 2 years, and I'm thinking maybe there's, 50-50. So I might not, kind of like a coin toss, not sure. So I'm kind of on the border there between whether or not I'll do it. But if I had to estimate the chances that my new puppy is going to cause my dog now, Chester, to be jealous, now I'm going to estimate that at 99.9%. So that's almost guaranteed that my current dog will be jealous. So personal opinion approach, another example maybe is doctors. So when doctors diagnose a patient and think about their chances of recovery, they might use their own experiences, personal opinion, and include that as they're sort of trying to figure out the chances of success in a treatment. So that's it for personal opinion approach, just based on experience, personal opinion. So subjective, open to interpretation based on who's deciding. All right, so we're done with that approach. Next, we'll talk about the relative frequency approach to probability, and this is also called experimental or empirical probability. So you can think of it as based on evidence. And this approach is going to be an estimate. And let's take a look at this example. So I looked at the 2021 baseball season and baseball player here, Trey Turner, and we were going to see if we could estimate the chances that when he goes to bat, he gets a hit. So if I only have to go on, the only thing I have to go on is how he's performed in 2021, then I would be using his data from 2021 to estimate what will happen moving forward. So here's what I found out, that he went to bat 595 times in 2021. He had 195 hits, and we will calculate his batting average, which will be our best estimate of the probability that he gets a hit the next time he is at bat. So this notation, so the probability of an event happening, and you'll see an E there. I did H to stand for hit. We usually use capital letters of the alphabet to represent some event occurring. So the probability that he gets a hit, we would just figure out how many times he had a hit and divide it by the number of times he went to bat. So this formula, I'm just going to write it with that notation. So this formula, the probability of an event, you look at the frequency of that event happening, whether it's in an experiment or in the past, the frequency of that event getting a hit, and then N here is going to represent the total number of trials or observations. So N for number of, in this case, the number of times he went to bat. So that's called the relative frequency or experimental approach to probability. And let's fill in these values. So he had 195 hits. He went to bat 595 times. And then I'm going to write that as a decimal first. So 195 divided by 595. Now I'm going to do 3 decimal places. That's often what they do in baseball. So 0.328. So 3 decimal places. So that's a batting average of 328. So that's the decimal form, but the directions here say round to the nearest 1/10 of a percent. So the reason I did the 3 decimal places is, remember, to change to a percent, you move the decimal to the right, 2 places, and then you add your percent symbol. So that would be 32.8%. So I estimate that the next time he goes to bat, he'll have a 32.8% chance of getting a hit. So this is always an approximate. We just write the equal sign to make our lives easy, but everybody understands this is an approximation if we're talking about the next time he goes to bat. All right, so let's just do a couple more here. So what if 13 out of 50 emails in your inbox are junk emails? What is the experimental probability that your next email is a junk email? All right, so again, we're using what's happened in the past to estimate the chances of an event happening in the future. So probability, and then we say probability of, and since it's junk email, I'll just do J for junk, probability of junk email. So it's frequency over N. So we look at the number of times you got junk email before. There were 13 out of the total number of emails that you got overall, 50. And then again, fractional answers are okay if you're asked for the fraction answer, or you could be asked for the decimal version. That would be 0.26 chance, or you could be asked for the percentage. So any of these 3 is correct. We would just follow the directions and be told which version we should be giving. So for the rest of chapter 4, I'm not going to write all 3 versions of the probability all the time. We'll just make our lives easy and pick maybe one of these to write, and then you'll just follow directions on which version they want, fraction, decimal, or percent. All right, so let's do number 3. I have a bag of 250 M&Ms. For our experiment, we're going to randomly sample 15 of them, and we find out in that group of 15, 3 of them are red. All right, so here's basically the idea. I don't want to go through 250 M&Ms and count to find out how many are red. So we're going to do our little experiment here. And it says, based on this experiment, what is the probability of selecting a red M&M from the bag? So the probability of getting a red based on this experiment, so frequency over N, in this experiment, 3 were red out of a total of 15 M&Ms. And I will go ahead and write this one actually again in the 3 forms. So I'm typing that in, and that's 0.2. I like to put the 0 on the end. So when I move my decimal there, it looks like my 20%. So I estimate here, based on the sample, I'm thinking that 20% of the 250 M&Ms are red. So when we use samples to estimate what's true about a population, this is always an estimation process. And again, we're just not interested in counting all of these M&Ms. So by taking a sample, this will be our best sort of idea of what would happen if we did so. So that's why it says, based on part A, how many of these 250 M&Ms do we think will be red? All right, so we need to find 20% of the, so 20% of the 250. So to find that proportion, we can take the decimal version there of 20%, 0.2. So that portion of the 250, so you multiply to find the proportion of a number. So we'll just take 0.2 times 250, and that tells me 50. So I'm just going to write here. So I estimate that 50 out of those 250 are red. So as we move forward in the semester, this is what we spend a lot of time on. We use known sample data to predict what we think is true of a whole population, in this case, the whole population of envelopes.